A modern city goes dark in a matter of seconds. Wide-scale grid failure typically begins with a single localized shock that cascades through the system. These failures trace back to sudden transient events. A power plant loses a synchronized generator, or a lightning strike causes a rapid voltage sag through a single line-to-ground fault. The grid survives these shocks through power system stability. This is the fundamental ability of interconnected synchronous machines to maintain their shared rhythm and return to a steady state after a disturbance. Engineering standards categorize stability based on the size and timing of the shock. Our focus is on the most violent category, large disturbance transient rotor angle stability. During an unstable transient, the grid physically desynchronizes. The heavy rotating machines that generate power lose their magnetic lock with the rest of the system, resulting in a total loss of coordination. Understanding grid collapse requires viewing the electrical system as a massive, interconnected mechanical web. In Elgaard's analogy, synchronous generators are heavy weights, and transmission lines are elastic strings holding the network in tension. Routine load changes act like minor vibrations. The strings stretch slightly, but the weights eventually settle back into place. This is small signal stability. Transient stability involves a massive, catastrophic shock. A transmission line fault acts as a blade slitzing through one of the primary elastic strings holding the network together. When a string is cut, the surviving lines must instantly stretch to absorb the massive shift in tension and fluctuating force. If the remaining lines cannot absorb the weight, they snap, and the mass falls entirely. In a power system, this physical drop represents a generator losing synchronism and being ejected from the grid. The physics of grid survival are decided on the multi-ton steel shafts of these generator rotors. A continuous tug-of-war occurs on this shaft. Mechanical torque, T sub m, drives the rotor forward, while electrical torque, T sub e, resists. Any mismatch creates a net accelerating torque, T alpha, physically forcing the rotor to speed up or slow down. This relationship is governed by the swing equation. It maps the rotor's physical acceleration to the difference between mechanical power input and electrical power output, divided by the machine's inertia, h. The accelerated variable is delta. This is the literal electrical angle between the internal rotor's magnetic axis and the rotating reference field of the grid. The swing equation is nonlinear because electrical power is tied to the sine of this angle. Because of this sine-delta nonlinearity, engineers cannot use standard linear tools to predict survival. They must mathematically track the physical swing of the rotor to see if it remains within stable limits. To solve for a single machine's survival, engineers simplified the chaotic complexity of the national grid. They used the single machine infinite bus model, or SMIB. The infinite bus acts as a perfect, unyielding voltage reference. It represents the collective strength of the rest of the grid, which cannot be shifted by our single generator. This chart shows the SMIB power angle curve, visualizing how much electrical power the generator pushes into the infinite bus at any rotor angle. At steady state, the mechanical power input perfectly intersects the electrical sine wave, finding equilibrium at a stable initial angle. If a sudden load increase occurs, the mechanical power line shifts upward. Exceeding electrical output, the rotor physically accelerates forward. The angle increases, climbing the sine curve, until electrical power matches the new mechanical power, settling into a new synchronous equilibrium. As long as the required power does not exceed the absolute peak of the sine curve, the rotor will find a new stable point and survive the disturbance. A load jump is a manageable stress. A short-circuit fault is a catastrophic shock. We analyze this by upgrading our SMIB model to feature two parallel transmission lines. A fault strikes one branch. The short circuit causes the grid voltage to plummet. Electrical power output drops to merely zero. While electrical resistance has vanished, the turbine continues forcing mechanical power into the shaft. This massive imbalance causes violent, unchecked rotor acceleration. On the power angle graph, the electrical sine wave collapses towards zero. The mechanical power line is now stranded far above the machine's electrical capability. As the rotor angle rapidly advances, it accumulates massive kinetic energy. This is the acceleration area, A1. Automate and command high-voltage circuit breakers to physically sever the damaged line. Opening the breakers isolates the fault. Electrical power is restored, but onto a new, lower sine wave, because the grid has lost one of its parallel lines. Even with the fault cleared, the crisis continues. The multi-ton rotor still carries terrifying forward momentum that must be arrested before the machine desynchronizes. Driven by its own momentum, the rotor continues swinging forward until it reaches a zone where electrical power is greater than mechanical power. This is the deceleration area, A2. Here, the grid acts as an electromagnetic brake, stripping kinetic energy out of the rotor. The equal area criterion states the generator stabilizes only if the available deceleration area is greater than or equal to the acceleration area. The specific angle where the breakers opened is the clearing angle, delta C. If breakers take too long to open, the red area grows. The absolute limit is the critical clearing angle, where the red acceleration area perfectly consumes the maximum braking area. Opening the breakers past this critical angle is futile. The rotor will slip a pole, completely lose its magnetic lock with the grid, and be violently ejected from the system. Engineers translate this maximum angle into a critical fault clearing time. Grid survival is decided in strict fractions of a second. This exact mathematical limit dictates the design and calibration of every protection relay and high-voltage breaker on the modern power grid. Grid survival depends on a microsecond race between mechanical inertia and protective relaying, a contest dictated entirely by the mathematics of the equal area criterion.